Good evening, ladies and gentlemen. I'm Steven Villagrasa, and I'm the 2009 CSUN FSAE Powertrain Crew Chief, as well as being in charge of the engine internals, cooling, fueling, and lubrication. This is Gustavo da Silva. He's in charge of the intake manifold. Sri Prajapati, who's in charge of the exhaust system, and Fabian Martinez, who's in charge of the drivetrain. I will give you a little overview of what the powertrain does. The engine internals relates to the moving parts inside of the engine to make it go. The cooling, fueling, and lubrication make the engine run and run reliably. The intake manifold is a piece used to direct air into the engine for combustion to take place. The exhaust system removes spent air from when combustion is finished. And the drivetrain transfers energy produced by the engine from the engine to the ground. The department goals for the 2009 FSAE team are to reduce weight and rotational inertia, specifically with rotating parts. That has to do with the drivetrain, which Fabian is in charge of, and also with a possible lighter intake manifold. We also want to increase power by correctly placing the power curve with the torque increase through correctly specified camshafts, since the track is relatively tight with few straightaways. And finally, we want to increase reliability through design refinements and unchanged designs, and thorough testing on new designs. As I mentioned, I'm in charge of the engine internals. In previous years, CSUN has used the 2003 to 2005 Yamaha R6 motorcycle engine. It's naturally aspirated, is a 4-cylinder, it originally had 105 horsepower and a weight of 140 pounds dry, and it was used from 2005 to 2008. The first fundamental choice for the team was a decision between different amounts of cylinders, as well as the advantages that each one offers. The most realistic options for CSUN are the 1, 2, and 4-cylinder engines. 1 and 2-cylinder engines are generally poorly balanced. However, the 4-cylinder tends to have a very good power to weight ratio due to its CSUN's past experience with the 4-cylinder was another strong point to consider when selecting an engine. The CSUN team's best engine options are as follows. The best suited single-cylinder engine are the Technique F1 250cc kart engine with 40 horsepower, 20 foot-pounds of torque, and a weight of 37 pounds dry. However, unlike the other engines, it does not have a transmission. The most appropriate 2-cylinder engine for our application is the Aprilia SXV 550cc supermoto engine with 66 horsepower, 27 foot-pounds of torque, and a weight of 72 pounds dry. The best 4-cylinders for our applications are the Honda CBR 600RR and the Yamaha R6 YZF 600. Both have around the same power and torque, but our team has more experience in previous years with the YZF 600, and our team has developed many high-performing engine parts for it. One strong performance increase that was considered is force induction, namely supercharging and turbocharging. A supercharger is available at no cost to us, which is very important in our considerations. However, it's costly to implement it, it's complex, and requires a large amount of tuning time in order to retain reliability, and which in turn goes against the overall team goal of lowering weight and increasing simplicity. Another area where torque increase can be found is to increase the piston stroke. This would provide a sound torque increase. However, the amount of torque increase would not be large enough to justify the increased cost and decreased time between rebuilds. So the goals for the internal parts of the engine are as follows. To reduce the internal friction of the engine, increase power and torque through the use of correctly specified camshafts, and ensure the reliability with the top-end rebuild. In 2008, the CSUN Formula SAE team developed some new camshaft profiles, since the original camshaft profile was developed for the power curve to remain at the upper end of the wheel. The cam profiles developed by CSUN in 2008 were made to lower the area where the peak power and torque are gained. The engine cylinder head will receive a racing preparation in order to optimize and ensure reliability for all the moving parts. The valves will be lapped in to ensure compression ratios as high as possible. New gaskets and seals will be installed on the top end of the engine, and the valve spring rates tested and selected at the lower end of the allowable range to reduce parasitic drag on the camshaft. And the bearing tolerances will be at the upper end of the allowable range to reduce friction. Our proposed design for the engine will be the reliable known Yamaha R6 motorcycle engine using torque-biased camshaft profiles and rebuilding and optimizing the cylinder head. I'm also in charge of the engine cooling, fueling, and lubrication. Problems our team has run into in the past are oil starvation, excessive cooling weight from improperly sized parts, and fuel pickup problems. The goals for the fueling, cooling, and lubrication are to increase reliability, decrease oil starvation, and maintain ease of assembly and manufacture. For the last 2 years, CSUN has used an aluminum radiator that has proved to be sufficiently reliable for the competition. In 2019, we'll continue to use this radiator for lightweight and good cooling capabilities. Another returning part to the cooling system will be the small 9-inch cooling fan with curved blades, since the cooling of the engine was sufficient. An area where previous teams have explored improvements was the water pump size. The 2005 team tried a car-type water pump with success. However, the added weight was not worth the additional water flow rate through the cooling system. The years between then and now have used the original Yamaha R6 water pump with success and less weight, and will remain the same. In 2005, a dry sump oiling system was added in order to prevent oil starvation. However, this solution adds weight and complications to the manufacturing process. A lighter and more practical solution to this problem is to retain the original oiling system and adding oil pan baffles, preventing slosh, as well as starvation. Fuel delivery system will remain stock since no reasonable weight loss or performance increase solution has been discovered. In recent years, as I mentioned, the fuel starvation was a problem. However, this was due to the lateral acceleration in turns. Solutions have included check valves, foam, and a large fuel pickup. The best solution from these options was found to be foam and a large fuel pickup. The smallest fuel tank possible will be used in order to keep weight low. So the proposed design for the cooling, fueling, lubrication is as follows. The radiator will have shrouds in front aluminum and behind copper fiber for the best cooling. The fan used will be the reliable Spall model. The original water pump that Yamaha makes will be used. The oil pan will have baffles to prevent slosh and starvation. The fuel delivery system will remain original, and a large fuel pickup with foam will be employed in the fuel tank. That concludes the engine internals, fueling, cooling, and lubrication. Now Gustavo will talk about CSUN's FSAE intake method.